Hello everyone. In today's lecture we will move to a new chapter, which is the design of digital infinite impulse response filters, the IIR filters. As we've said before, a filter is an LTI system that is designed basically to allow a certain band of frequencies to pass, which is called the pass band, and stops all other frequencies, which is called the stop band. And the filter design process basically is trying to find a practically realizable filter whose frequency response approximates the desired ideal frequency response. And as we have seen in the previous chapter, there are two types of digital filters, FIR filters and IIR filters. We have already covered the design of FIR filters in the previous chapter, and in this chapter we're talking about today, we will discuss the design of infinite impulse response filters. In general, any IIR LTI system can be represented by the following LCCDE, which is simply saying that the present value of the output y of n depends on two terms. The first term is a summation of the previous outputs, which means we have a feedback, and the other summation depends on the present and previous values of the input. And this is a signal flow graph of an IIR system, and as you can see, the input x of n is applied to the system, multiplied by constant b0, and then delayed, multiplied by b1, another delay multiplied by b2, and this part corresponds to the feed-forward part. Whereas this part of the filter corresponds to the feedback part, where the output y of n is fed back into the system and multiplied by a constant, and then another delay multiplied by a constant. Add all of these will give you the feedback part of the equation. The system function of a causal, stable, and realizable IIR filter need to be of a certain form. It need to be represented as follows. So, since the filter is known to be causal, so the impulse response h of n should be 0 for n less than 0. So computing the system transfer function, or the z transform of the impulse response, it will be summation from n equal to 0 up to infinity h of n z to the power minus n. Again, we are starting from n equal to 0 because we're talking about causal filter. For causal filters, the impulse response h of n is 0 for n less than 0. And for this transfer function to be realizable, it needs to be of the form of a rational function. In other words, a ratio between two polynomials, which is the form we have discussed in the Z transform chapter. So we have a polynomial of z minus 1 in the numerator, another polynomial of z minus 1 in the denominator. And these two polynomials can be factorized in terms of first order terms of the form 1 minus zk times z minus 1, which correspond to the zeros we have in the system. And the denominator is also factorized into first order terms of the form 1 minus pk times z minus 1, which corresponds to the pools we have in this filter. So for causality, again, h of n, the impulse response, is equal to 0 for n less than 0. And for the system to be both causal and stable, as you remember, we had this discussion in the Z transform chapter, all pools must be inside the unit circle in the Z domain. In other words, magnitude pk should be less than 1 for all k, for all pools. All pools need to be inside the unit circle, and the region of convergence needs to be going outward up to infinity. When this is satisfied, we would have a causal and stable filter. And the zeros can be anywhere. The design objective here is to find the coefficients ak and bk so that the frequency response h of e to the power j omega approximates the ideal desired frequency response. And as you remember from the Z transform chapter, the frequency response is simply the system transfer function h of z evaluated at the unit circle, modulus z equal to 1. Generally, the techniques used to design IIR filters are based on employing the continuous time filter design methods. In other words, when we design a digital IIR filter, we start by designing a continuous time filter, and then we use a continuous time to discrete time transformation to transform the continuous time filter we have into a digital IIR filter. Therefore, we will start to talk about continuous time filters. So, in order to have a stable, causal, and realizable continuous time filter, the system transfer function h continuous of s needs to be of this form. First of all, h continuous of t is the impulse response of the continuous time filter, and h continuous of s is the system function, which is the Laplace transform of the impulse response. And since we are talking about causal filters, again the impulse response h continuous of t must be 0 for t less than 0. That's why when we apply the definition of the Laplace transform, the integration starts from 0 up to infinity of h continuous of t e to the negative st dt. Of course, s is the complex frequency, the Laplace transform over here, and s is equal to sigma plus j omega. And as you remember, we'll use capital omega or uppercase omega in case we are talking about continuous time systems, and lowercase omega when we talk about discrete time systems. So, when you compute the system function, it should also be of a rational form, ratio between two polynomials. In the numerator, polynomial of the parameter s, and in the denominator, another polynomial of the variable s. And the polynomial in the numerator can be factorized into this form: first order terms multiplied together, s minus zeta k, where zeta k represents the zeros we have, and the denominator as well can be factorized into this first order terms multiplied together, s minus sk, where sk corresponds to the pools we have over here. So again, the causality requires that h continuous of t, the impulse response, must be 0 for t less than 0. And for the system to be both causal and stable, all pools must be on the left half plane of the S domain. In other words, all the real part of the pools sk must be negative, must be less than 0 for all k. And the zeros can be anywhere. So, in order to ensure that the frequency response h of j omega goes to 0 as omega goes to infinity, it's required that the number of zeros must be less than the number of pools. So, how can we get the frequency response h of j omega from h of s? Since s is simply sigma plus j omega, we can set sigma to be equal to 0. In other words, we can evaluate h of s along the imaginary axis. This will give us the frequency response, which is similar to what we have done in the Z domain. Evaluating the system transfer function h of z along the unit circle would give us a frequency response of a discrete time system, but in continuous time systems, computing h of s along the imaginary axis, the j omega axis, where sigma is equal to 0, this will give us the frequency response. And we need to make sure that the number of pools is always larger than the number of zeros in order to make sure that the response, the frequency response, goes to 0 as omega approaches infinity. And now we can observe some similarities between h continuous of s and h of z. Both are rational functions, both are having pools and zeros, both have conditions on the pools for causality and stability. For a discrete time system to be causal and stable, all pools must be inside the unit circle. And for a continuous time system to be causal and stable, all pools must be in the left half plane of the S domain. And also note the similarity between the unit circle in the Z domain and the j omega axis in the S domain. when we compute h of z along the unit circle, we get the frequency response. When we compute h of s along the j omega axis, we get the frequency response. So there is correspondence in a way between the unit circle in the z domain for discrete time systems and the j omega axis for continuous time systems in the s domain. And we're going to talk about this later on. We will talk about the transformation from continuous time systems into discrete time systems. So, the steps of designing an infinite impulse response filter goes as follows. First, we will start with the specification of a discrete time filter. You will be asked to design a discrete time digital IIR filters with this kind of specification. First step, you need to convert this specification into continuous time specification. And as you remember, in the previous chapter, we talked about the absolute specification, relative specification, and analog specification or continuous time specification, epsilon and A. And we have seen equations relating epsilon and A to AS and AP. And this step depends on the transformation which will be used in step 3, the transformation from continuous time to discrete time. As we have said before, we will start by designing a continuous time filter, and then we will transform this continuous time filter into a discrete time filter. So the first step is to convert the discrete time specification we have into continuous time specification, and here we need to take care that we need to consider what kind of transformation we will use later on in step 3, because this will affect the frequency in a way. And as we're going to see later on, when we use the bilinear transformation, we will need to adjust the frequencies in a certain way when we are transforming the discrete time specs into continuous time specs. The next step is to design a continuous time filter, in other words, to obtain H continuous of S, that basically satisfies the requirement we have for the continuous time filter. The third step is to convert this continuous time filter, H continuous of S, into a discrete time filter, H of Z. And this is done using a continuous time to discrete time transformation. And there are two types of continuous time to discrete time transformations. One is called the impulse invariance transformation, and the other one is called the bilinear transformation. We will talk about them later on. So the process goes as follows. Given the specification, we have a digital IIR filter specification. We transform these into continuous time filter specification. And then we design a continuous time filter, get H continuous of S, and then transform this continuous time filter into a discrete time filter through either the impulse invariance or the bilinear transformation, and now we can get our H of Z, which corresponds to an IIR filter. Again, we will be focusing on low-pass filters because basically we have transformations that will transform a low-pass filter into other types of filters. So for other filters, such as a high-pass filter or band-pass filter or band-stop filter, we can use the so-called frequency band transformations, which basically transforms a low-pass filter into a high-pass filter or a band-pass filter or a band-stop filter. And these frequency band transformations can be performed on the continuous time filter or on the discrete time filter. Causal infinite impulse response filters cannot have linear phase because, as we have discussed in the previous chapter, the phase linearity is related to the symmetry in the impulse response. And since we have a causal IIR filter, the impulse response is 0 before 0, which means we cannot have this symmetry in the impulse response, and hence we cannot have a linear phase causal IIR filter. So, the advantages of an FIR filter are mainly that it has a linear phase, it's always stable because there is no feedback and there are no pools, and it can be realized efficiently in hardware. But the disadvantages of FIR filters are basically that they always require a much higher filter order compared to an IIR filter with the same specification. So if we have the same specification and we build an FIR filter and we build an IIR filter with the same specification, the FIR filter will require much higher order filter. And by higher order, we mean a longer filter with larger hardware and so on. This will basically affect the performance as follows. First, the delay in the output response will be much greater than that of an IIR filter, will have larger delay, and also the cost of the FIR filter will be higher compared to the IIR filter since it's having a higher order. And also the design method for FIR filters are kind of iterative. If you remember, we start by designing the filter, checking the specification. If it's not satisfied, we go to increase the length of the filter, check again. If the specs are not satisfied, we use a different window, and so on. So it needs kind of iteration, and sometimes we can use a computer-aided techniques in order to do these iterations. So even though the FIR filters has many advantages, but for most applications IIR filters are desirable because you will be having a lower order filter, less hardware, lower cost, and so on. Unless the phase linearity is a requirement for your design. So if you need to have a linear phase, if it's an essential part of your design, then you must use FIR filters. And also there is this category of filters that's called adaptive filters, filters which change their response based on the channel or based on a certain parameters. These kind of filters are usually preferred to be FIR because changing the filter response will not affect the stability of the system since FIR filters are always stable. But if you have an IIR filter which is adaptive, changing the parameters of the filter might result in an unstable filter. So these are the specifications we have discussed before. The relative specification, AP, the passband ripple, and AS, the stop band attenuation. And here we have the analog specification, which is 1 over 1 plus epsilon squared and 1 over A squared. If you remember from the previous chapter, we used to call this 1 over square root of 1 plus epsilon square, and this we used to call it 1 over A. What's the difference here? The difference here is that we are plotting the magnitude squared of h of j omega. In the previous chapter, the plot was for h of j omega magnitude. Here it's squared. That's why we have removed the square root over here, and this now is A squared. So, the analog or continuous time filter specification, basically we use epsilon and A to represent the ripples in the passband and the stop band attenuation. So if we go back over here, we can see that this level, which is 1, corresponds to 0 decibel, and now we would allow this kind of ripple in the passband, which is AP decibels below 0, and in analog specification this corresponds to 1 over 1 plus epsilon squared. So 10 log 1 over 1 plus epsilon squared would correspond to minus AP. In other words, AP would be equal to 10 log 1 plus epsilon squared. So as you can see over here, we can write AP as 20 log square root of 1 plus epsilon squared, which is equivalent to 10 log 1 plus epsilon squared. And from this equation, we can write epsilon in terms of AP. So AP over 20, 10 to the power AP over 20 minus 1 under square root to give you epsilon. Same for AS. If you go back over here, you can see that the level AS, which is how many decibels we go below 0 in the stop band, corresponds to 1 over A squared. So again, minus AS would be 10 log 1 over A squared, which is minus 20 log A. Therefore, we can write AS as 20 log A, and now we can write A in terms of AS as A equals 10 to the power AS over 20. And basically we have discussed this kind of conversion from discrete time specification to continuous time specification in the previous chapter. Here we are just refreshing our knowledge and information. So again, the ideal frequency response should be flat for the entire passband, flat for the entire stop band, with a sudden transition between passband and stop band. But physical and actual circuits cannot provide this constant transmission during the passband. That's why the specification allows for a deviation from this passband, which is ideal level 0 decibel, within an upper bound of AP, which is the passband ripples. So basically we're saying here we would allow sort of fluctuation in the passband, and instead of ideally having a flat passband, would allow sort of ripples within AP decibels. That's why we call AP the passband ripple. And depending on the application, the value of AP might go from 0.05 decibel up to 3 decibels or so. Similarly, in the stop band, ideally we need to provide a flat response with the gain of 0, which corresponds to minus infinity attenuation. But the specification allows for a certain transmission over the stop band because physical circuits cannot achieve this kind of flat 0 response in the stop band. That's why the specification allows for an attenuation of AS in the stop band. And instead of having 0, which corresponds to minus infinity attenuation, would allow finite value of stop band attenuation AS, which might be 20 decibel, 30 decibel, up to 100 decibel, depending on the application we have. And again, we cannot have a sudden change between passband and stop band. That's why we need to have sort of a transition band over which the frequency response transitions from the passband gradually into the stop band. And here we have defined before omega p and omega s, omega p being the edge of the passband and omega s being the edge of the stop band. But remember that in the previous chapter we used lowercase omega p and lowercase omega s because we were talking about designing digital filters, and we use a normalized frequency lowercase omega. But here we are talking about designing continuous time filter and then transforming it back into digital filter. So in this part we are discussing the design of continuous time filters. That's why we use the uppercase omega. So omega p is the passband edge, omega s is the stop band edge. The ratio omega s over omega p is usually called the selectivity factor of the filter, omega s over omega p. And for an ideal filter with an abrupt change between the passband and stop band, omega s equals omega p, and hence this selectivity factor is 1. But for practical filters, omega s is larger than omega p, and selectivity factor will be slightly higher than 1. So the passband transmission is specified to be 0 decibel, which means it's a passive filter. In other words, the signal will pass as is, it will not be amplified. But the final filter can be given a passband gain by adding sort of an amplifier, using operational amplifier or transistors and so on. So the parameters of a low-pass filter are mainly 4. The edge of the passband, omega p, edge of the stop band, omega s, the maximum allowed variation in the passband or the passband ripple, AP, and the minimum required stop band attenuation, which is called AS. The same 4 specifications we had when we were designing digital FIR filters. So for this specification to be as close as possible to ideal response, we need to reduce the ripples in the passband, we need to increase the stop band attenuation, and we need the selectivity factor omega s over omega p to be approximately 1. However, if we try to achieve this, we'll be getting closer and closer to an ideal filter, which will be of very high order. It will be a complex circuit and expensive, and will have its own problems. Okay, so what about the phase response of the filter? Up till now we have been talking about the magnitude response of the filter. What about the phase response? The filter design problem becomes very complicated when both magnitude and phase responses are specified. That's why generally we will ignore the phase response and we will not have any specifications related to the phase response. So, given the filter specification, we need to design a filter whose transfer function has a magnitude that meets these specifications in terms of omega p, omega s, ap, and as. Generally, in literature, we have 4 types of analog filters: the Butterworth filter, Chebyshev type 1 filter, Chebyshev type 2 filter, and elliptic filter. And today we will learn about the Butterworth filter and how to design continuous time Butterworth filters. Butterworth filters exhibit what's called a monotonically decreasing transmission. In other words, it does not have any ripples. In order to understand this, let's move on a little bit to look at this curve. But before we do so, please note that this curve has a mistake over here. This should be magnitude h of j omega, not squared. It should not be squared, so please ignore this square over here. So it's only magnitude h of j omega. So as you can see, the frequency response of Butterworth filter is monotonically decreasing. It decreases gradually without any fluctuations, without any ups and downs. So there is no fluctuations in the passband, no fluctuations in the stop band. As the frequency increases, the magnitude response decreases. This is what we call the monotonically decreasing response. So it has a monotonically decreasing transmission, i.e. there is no ripples, and all the transmission zeros, all the zeros of this filter are happening at omega equal to infinity. So it's called an all-pool filter, as if it has no zeros. The magnitude function of an nth order Butterworth filter with a cutoff frequency omega c is given as follows. Magnitude, the frequency response squared, is equal to 1 over 1 plus omega over omega c to the power 2n. What do we mean by an nth order Butterworth filter? It simply means a Butterworth filter which has n pools. The order of a filter is equal to the number of pools it has. So if we say a second order Butterworth filter, it's a Butterworth filter with 2 pools. If we say a fifth order Butterworth filter, we mean we have a Butterworth filter with 5 pools, and so on. And omega c is the cutoff frequency, and this is the magnitude squared of the frequency response, 1 over 1 plus omega over omega c to the power 2n. Omega is a frequency variable, and omega c is a constant, which is the cutoff frequency. And as we can see over here, this is the normalized frequency, omega over omega c, normalized with respect to the cutoff frequency. So here, this one represents omega equal to omega c. And at this frequency, the magnitude response is always 1 over square root of 2. If you go back to this equation and set omega to be equal to omega c, this term would be 1. And the magnitude squared is 1 over 2, which means the magnitude is 1 over square root of 2. So again, please keep in mind that there is a mistake over here, and this is only the magnitude of the frequency response, not the magnitude squared. So all the Butterworth filter, whatever the order as is, will have a gain of 1 over square root of 2 at the cutoff frequency, and I guess we have seen this kind of situation in circuits. And as the order increases, the filter approaches the ideal filter. This dotted frequency response corresponds to an ideal low-pass filter with an abrupt change between the pass band and stop band. So this curve corresponds for n equal to 1, a first-order filter, second-order filter, third, fourth, fifth. As n increases, approaching infinity, the Butterworth filter would approach an ideal low-pass filter. So increasing n would result in the curve approaching that of an ideal filter. And at omega equal to omega c, you can see that the magnitude of the frequency response is always 1 over square root of 2, regardless of the filter order. Omega c is called the cutoff frequency, or the 3 dB cutoff frequency. And 3 dB because if you take 20 log 1 over square root of 2 or 10 log 2 will give you 3 decibels. We note that the characteristic is monotonically decreasing. In other words, there is no ripples in the pass band or the stop band. And the maximum value of the frequency response is happening at omega equal to 0. As you can see over here, the maximum gain, which is 1, is happening at omega equal to 0. And the smallest gain happening in the pass band would be at omega p, since it's monotonically decreasing. So at the edge of the pass band will be the smallest gain happening in the pass band. So the maximum deviation in pass band transmission from unity occurs at the pass band edge, i.e. at omega equals to omega p. Towards this end, we will be having a derivation, which I will skip for now. I will jump to the final result over here. Here we're trying to relate the specifications we have, AP, AS, omega P, and omega S, and the filter order. And the final result would look like this. First, we will define a quantity called alpha, which is omega S over omega P, the ratio between the stop band frequency and the pass band frequency. And this ratio we have called before the selectivity factor. And we will define another quantity which we'll call beta. It's basically square root of a squared minus 1 over epsilon. And using the previous equations we have, we can relate A to AS and epsilon to AP. So if we employ the previous equations we have seen before, we will find that beta is equal to square root of 10 to the power AS over 10 minus 1 and over 10 to the power AP over 10 minus 1. Using these two quantities, we can get the value of n, which is the number of poles we have in a Butterworth filter, the order of the Butterworth filter, in order to meet these specifications, AS, AP, omega P, and omega S, and n should be larger than ln beta over ln alpha, where n should be an integer. So usually this ratio will give a fraction. We will use the next higher integer. Of course, this is based on a derivation we have skipped, but again, these are the final results, which relates the filter specification AS, AP, omega S, and omega P to the filter order. And supposedly, a Butterworth filter with this kind of order will meet these specifications. So, in order to find the cutoff frequency omega C, because it's an important part of the design process, we need to find omega C. So again, we have a derivation which we will skip for now, and we'll find that the proper value of omega C should be equal to omega S, which is the edge of the stop band, over a squared minus 1 to the power 1 over 2n. A is the stop band attenuation in ratio, and AS is the stop band attenuation in decibel, and we have a relation between A and AS, and n capital is the order of the filter. So omega C is related to the order of the filter, to the stop band attenuation, and edge of the stop band. In MATLAB, we have two commands that will help us to get these results, Butterworth and butter. And this can be used as follows. Butterworth computes the order n and the cutoff frequency omega C. So you start by AP, AS, omega P, omega S, and we have seen the equations from which we can compute n and omega C, and the command Butterworth directly computes the order n and the cutoff frequency omega C, given AP, AS, omega P, and omega S. The other command, butter, provides the numerator and the denominator polynomials of the filter transfer function. If you remember, h continuous of s must be of a rational form, ratio between two polynomials. So the command butter would provide the polynomial in the numerator and the polynomial in the denominator as well. So now that we have the filter order n and omega c, which is the cutoff frequency, now we can compute the pools, the location of the pools. And again, we will not go through the details, but the pools of an nth order Butterworth filter are shown over here. They are uniformly located on a circle whose radius is omega c, this circle is happening in the S domain or the S plane. So S is a complex frequency, it's sigma plus j omega, and here there is a mistake, this should be uppercase omega, j capital omega, and the poles we have are uniformly placed on the half circle located in the left half plane of the S domain. Why is the left half plane of the S domain? This is the condition for the system to be both causal and stable. For a continuous time system to be both causal and stable, all poles must be located in the left half plane. And through a mathematical derivation which we will not go through, the Butterworth filter would have its poles located on this half circle located in the left half plane of the S domain, and the poles are separated by an angle pi over n, where n is the order of the filter or the number of poles we have. And the first pole, P1, will be shifted by pi over 2n from the j omega axis, and the circle radius is omega c. So note that the poles lie on a circle of radius omega c. Omega c is the pole frequency or the 3 dB frequency or the cutoff frequency at which the frequency response is 1 over square root of 2, and we had an equation to compute it in terms of a, n, and omega s. The poles are uniformly spaced on this circle and are separated by equal angles of pi over n, with the first pole at an angle pi over 2n from the j omega axis. And the next few figures will show the position of the poles for a Butterworth low-pass filter for n equals 2, 3, and 4. For n equals 2, we have two poles, so the poles are separated by angles pi over 2, which is 90 degrees. And as you can see, pole 1 and pole 2 are complex conjugate to each other. So a circle with radius omega c, and the two poles are spaced by an angle pi over n, and the first pole is spaced from the j omega axis by an angle pi over 2n, which is 45 degrees or pi by 4. If n is equal to 3, the poles would be separated by pi over n, pi over 3, in this case 60 degrees or pi over 3. Therefore, you will find we have one real valued pole, P2 is a real valued pole, and P1 and P3 are also complex conjugate poles. So the general case is that for n even, we will not be having any real valued poles, we'll only be having complex conjugate poles. But for n odd, we will be having only one real valued pole, and the remaining poles will be complex conjugate to each other. And for n equals 4, same applies. We'll be having P1 complex conjugate to P4, P2 complex conjugate to P3. The poles are separated by angle pi over 4, and again all are located in the circle of radius omega c. Once all the pole location has been found, we can write the transfer function as follows. So in the denominator over here, s minus the first pole times s minus the second pole, and so on until we get s minus the last pole we have. And this will give us a polynomial in the denominator of order n. Whereas a Butterworth filter is known to be an all-pole filter, doesn't have any zeros, or that all zeros are located at infinity. That's why we do not have any polynomial over here in the numerator, only a constant k, which is the DC gain, times omega c to the power n. And k is a constant that's equal to the DC gain of the filter. If it's not given, you can assume it to be 1. So, to summarize the previous steps, in order to design a Butterworth low-pass filter, we start with the 4 specifications we have. Edge of the passband, omega p, edge of the stop band, omega s, the passband ripple AP, the stop band attenuation AS. And first we compute the ratio omega s over omega p, or the selectivity factor, which we call alpha. Then we compute beta, and then n is larger than or equal to ln beta over ln alpha. It is the integer that's larger than this ratio. The next step is to determine the cutoff frequency omega c using the equation we've seen before, which is omega s over a squared minus 1 to the power 1 over 2n. Once we have n, the number of pools, and omega c, now we can determine the location of the n pools graphically. We'll draw a circle in the s domain. The radius of the circle is omega c, and we will locate the pools on the left half of this circle, which lies in the left half plane in the s domain, and the pools are separated by pi over n, whereas the very first pool is displaced from the j omega axis by pi over 2n. Once we know all of this, we can plug all the pools into this equation h of s in order to get the transfer function of a Butterworth filter that satisfies the specification we have started with. So here let's try to apply what we have learned so far to an example. We are asked to design a Butterworth analog filter with the following specification. 20 log, the frequency response should be between 0 and minus 6 dB from 0 up to 2 radians per second. Since this is a low-pass filter, we can see that this 2 omega radian per second is actually omega p, the edge of the pass band. And this minus 6 dB is minus AP, so the ripples allowed in the pass band AP is 6 decibels. And from 3 radians per second up to infinity, this would be the stop band. So 3 radians per second is omega s, the edge of the stop band. And in the stop band, 20 log magnitude h of j omega should be always less than minus 20 decibels, which means AS is equal to 20 decibels. So AP is 6 decibels, AS is 20 decibels. Next, we need to find epsilon and A to transform these specifications into continuous time filter specifications. So as we know, epsilon is the square root of 10 to the power AP over 10 minus 1. There is a mistake in this equation in the textbook. It should be 10 to the power 0.1 times 6 minus 1, which will give you 1.7266. This number is correct. And A is 10 to the power AS over 20, which will give you 10. So now we have epsilon and A. Now we can get alpha, beta, and then we can get n, the order of the filter. So alpha is the ratio between omega s and omega p, 3 radians per second over 2 radians per second, will give us 1.5. And beta is equal to the ratio between the square root of a squared minus 1 over epsilon, which will give us 5.7628. Now we can compute n as the integer which is larger than the ratio between ln beta over ln alpha. This will give us 5. So we have a Butterworth filter of 5th order, which has 5 pools. One of them will be located on the real axis with no imaginary part, and the 4 other pools will be complex conjugate to each other. And we can find the location of these pools graphically, but first we need to find the value of omega c, the cutoff frequency. And now we can use the equation we have seen before to find that omega c is equal to 1.8948 radians per second. This equation computes omega c in terms of omega s, a, and n. Now that we know omega c, we can find the pools graphically by simply plotting a circuit in the s domain. The radius of the circle is omega c, and locating the pools uniformly in the left half part of the circle. So let's go to our whiteboard over here. As you can see, we've drawn a circle whose radius is omega c, and all the pools are located on the left half plane of the S domain on this circle. And pool 1 is a complex conjugate of pool 5, and pool 2 is a complex conjugate of pool 4, and pool 3 would be real valued pool. And again, the separation between pools is pi over n, since n is 5 in this problem, so it's pi by 5. And the first pool is located at an angle pi over 2n, which is pi over 10 in this case, from the j omega axis. So the first pool would be simply a complex number whose magnitude is omega c and whose angle is equal to pi by 2 plus pi by 10. The angle of this complex number is pi by 2 plus pi by 10, which can be written using cosine and sine representation using Euler's equation. And P1 is the complex conjugate of P5. Similarly for P2, as you can see, P2 is a complex number whose magnitude is omega c and whose angle is equal to pi by 2 plus pi by 10 plus pi by 5. And this is equal to the complex conjugate of pool P4. So now we have found 4 pools out of 5. The third pool we have is a complex number whose magnitude is omega c, whose angle is pi by 2 plus pi by 10 plus 2 pi by 5. This will give us actually omega c e to the power j pi, which would basically be a real valued number and a negative number. Now we have the 4 pools. We can just put these together, s minus the first pool times s minus the second pool up to the 5th pool. We'll get a polynomial of 5th order, s to the power 5, and in the numerator over here we would have k times omega c to the power 5. K is not given, we can assume it to be 1, so here we will have omega c to the power 5. And now we have the transfer function of a 5th order Butterworth filter, continuous time Butterworth filter, which now is ready to be transformed into a digital filter. So again, designing an IIR filter always starts by designing a continuous time filter. And up till now we have learned how to design a continuous time Butterworth filter, starting with the specification, ending with the transfer function of a continuous time filter. And this can be done using MATLAB if you use Butterworth and Butter, and you will get exactly the same results. If you supply omega p, which is 2 radians per second, omega s 3 radians per second, AP 6 decibels, AS 20 decibels, and this S over here tells the command that this filter is happening in the S domain. In other words, it's a continuous time filter. This will give you a 5th order filter and the cutoff frequency exactly as we have computed. And using the command butter will give us the polynomials in the numerator and the denominator. This polynomial over here is the polynomial in the numerator, which is basically, it has no s in it, only the constant 24.422, which is this constant, which is omega c to the power 5. And in the denominator we have, this is the constant, this is s to the power 1, s to the power 2, s to the power 3, s to the power 4, s to the power 5. So it's basically s to the power 5 plus 6.13, s to the power 4, and so on. If you go back over here, you'll be having the same coefficients. So the command butter will give you the coefficients of the polynomial in the numerator and the denominator. This is another example. It can be done using MATLAB. So we have the edge of the pass band is 40 Hertz, edge of the stop band is 50 Hertz, AP 1 decibel, AS 30 decibel. Using Butterworth, you will get N to be 19, and the cutoff frequency will be omega c over 2 pi. And now we can get C and D, which are the coefficients of the polynomial in the numerator and the denominator. Generally speaking, Butterworth filters have kind of a standard transfer function. So all first order Butterworth filters would have a denominator polynomial of the form 1 plus s. And all the second order Butterworth filter will have a denominator polynomial of the form 1 plus 1.414s plus s squared, and so on. So this table provides what's called the prototype Butterworth filter. A prototype Butterworth filter is basically a Butterworth filter whose cutoff frequency is 1 radian per second and whose DC gain is 1. So the polynomials given in this table are for cutoff frequency 1 radian per second and DC gain of 1. In case you want to design a Butterworth filter of a different cutoff frequency. Like in the previous problem over here, you had a cutoff frequency of 1.8948, a different cutoff frequency which is not 1. Again, this table, the prototype transfer functions given here are for cutoff frequency of 1. So simply you need to replace S by S over omega C, and this will give you the Butterworth filter you are looking for. And I want you guys to try to do this. So let's go back over here. We have a 5th order Butterworth filter with cutoff frequency 1.89. So I want you to try to use this polynomial, which is for the n equal to 5, 5th order filter, and replace every S with S over omega C. And you will end up with this exact equation over here. So the design process over here can take different forms. I can ask you in the exam to find the location of the pools. So first you have to find the order of the filter, you need to find the cutoff frequency, you need to find the location of the pools, and then find the transfer function. Or I can give you this table and you can use it right away. If you want to design a 5th order filter, you would use this polynomial in the denominator, and then you would replace S by S over omega C being the cutoff frequency you want in your design. So let's try to do this on a 3rd order filter. Let's assume we want to design a 3rd order Butterworth filter with cutoff frequency omega C. First step, 3rd order filter, we will use this polynomial 1 plus S times 1 plus S squared. So this is a prototype Butterworth filter with cutoff frequency of 1 radian per second. In order to design a Butterworth filter 3rd order with a cutoff frequency omega C, you would simply replace S by S over omega C. So every S over here is replaced by S over omega C. Every S over omega C, and so on. And this will give you omega C to the power 3 in the numerator, and this kind of polynomial in the denominator. I want you to do it for the previous example where n was 5, and make sure that you can understand how to substitute S with S over omega C, and you will reach the same result. Now we have designed a low-pass filter. Now we can use what's called frequency band transformation to convert these low-pass filters into high-pass or band stop. This basically can be performed either on the continuous time filter or on the discrete time filter. But here we will learn about this transformation for continuous time filter. We will focus on transforming low pass to high pass or band stop in the continuous time filters. So this table summarizes it all. So starting with the prototype or the normalized prototype filter we have in the previous table, which has a normalized cutoff frequency of 1 radian per second. If you replace S by S over omega C, you will transform it from a low-pass filter with cutoff frequency of 1 radian per second into a low-pass filter with a cutoff frequency omega C. But again, if you use the prototype transfer function and replace every S by omega C over S, replace every S by omega C over S, you will get a high-pass filter with cutoff frequency omega C. And similarly for band pass and band stop, if you replace S with this equation, you will get a band pass filter. If you replace S with this equation, you would get a band stop filter. The critical part over here, you're substituting S in the prototype expression. The prototype expression which appears in this table. So we always start with this standardized table. Replacing S by S over omega C will transform this prototype filter from being a low-pass filter with cutoff frequency 1 radian per second into a low-pass filter with cutoff frequency omega C. Starting from this table and replacing S with omega C over S will give you a high-pass filter, and so on. So this is the frequency band transformation table. And in MATLAB, these transformations are implemented by the functions low pass to low pass, low pass to high pass, low pass to band stop. And this will be it for today's lecture. In the next lecture, we will learn about transforming this continuous time filter into a discrete time filter.